Dear ladies and gentlemen, thanks for the invitation to this conference to give you some insights in our recent results on magnetic parameters in reduced dimensions. First, I will shed the light on the spintronic impact on the market, which are up to now only MRAMs. Then I explain and concentrate on the phenomena of spin transfer torque, spin orbit torque, domain wall racetrack, and Skermian racetrack. Then I show you some Skermian systems and their variety. We have studied carefully magnetic parameters in one of these systems. Then I will make some comments of the magnetization of simple permalloy, and I show you our experience on magnetic van der Waals systems. The own published and not still published data presented here are based on the work of the people I have written here from our institute, the neighboring institute, the Academy of Science in Beijing and the Helmholtz Center in Berlin. Let's start with the MRAMs. You see here a typical design, I think everyone of you knows. And here are the real pictures, how they are integrated in CMOS technology. You see here a typical single device or a single element where you see strong morphology, different from here the FET structures prepared by ALD, I come to this later, which are much sharper. So the MRAM market looks at the moment, I hope I did not mistake in the following. You can buy MRAMs here via Amazon for 800 euros per gigabit, and the corresponding CMOS devices are more than a factor 100 cheaper. Very recently, IBM stated the following concerning the MRAM technology. These limitations of MRAMs are limited by two key challenges. One has to reduce the write currents and to increase the cell density. And if you ask yourself, should I buy MRAM stocks? At the moment, I would not prefer this. You see the Everspin, complete MRAM company. Here you see starting with very high values of the stock and slowly decreasing up to now. Now let's have a look into the basic physics of spin transfer torque. The first version was the parallel one, where two relatively thick coffee bean layers were separated by a 2 nanometer thick MgO. In the meanwhile, the perpendicular version is preferred, where the electrons are flowing perpendicular to the plane and insert due to spin transfer a change in the magnetization. But it is very hard to produce layers which have an out-of-plane perpendicular magnetization. This can be realized in that way. Normally we have here the MRAM element consisting of 13 elements, and you see here relatively thin coffee bean layers adjacent to a synthetic antiferromagnet. There are in some publications element distribution measurements presented, and you see here one example where you can realize that you have at the interfaces, or there are really no interfaces, you have a strong intermixing of the elements. And to summarize, the lattice appears to be strongly disturbed. You have a very strong intermixing of the element. Interfaces are not well defined, and this is correlated to the fact that the magnetism on the nanoscale is already not well known. So where does this come from? The normal preparation technique are magnetron sputtering. This is a high energy preparation, much higher than the other possibilities which are more expensive and slower, pulsed layer deposition and molecular beam epitaxy. So you have here an decreasing film quality with increasing energy impact. The advantage of the magnetron sputtering is all materials are possible. The drawbacks, they are non-conformal, strongly dependent on the actual deposition conditions, and post-annealing is often required. In the last 2 decades, another technique which is extremely interesting for semiconductor industry is the atomic layer deposition. This is a conformal deposition technique where you grow layers atomically smooth layer by layer, and you see here some examples of the layer quality. Advantages are well seen. They are conformal, atomically smooth, they have low energy impact, and we have a very high sample quality. But this cannot be used for metals because their deposition is extremely difficult. By the way, this is relatively slow technique, but the layers are very thin. And the ALD has an strongly increasing impact in all the semiconductor industries and increase the performance of the silicon-based devices or CMOS devices strongly. Since about more than 10 years, a new effect is on board, spin orbitalk, which works the following. In contrast to the spin transfer scheme, you have here a non-magnetic layer where the current runs through, and via spin orbit effect it transfers spin polarization into the free layer and can switch it. You see here the effect sketch, and in the same dimensions typical layer quality. One important parameter here is the spin diffusion length, which is strongly dependent, as you can see here, on the interlayer quality. And since the interlayer is not well defined, the spin diffusion length is also not well known, strongly spreading through the literature. And furthermore, the spin orbit effect itself, because it's a relativistic effect, is not well understood, and the important parameters not well predictable. So let's look here to the switching current of STT, SOT, STT elements. The requirements is from the electronic side, it has to be, if possible, below 10 to the 11 amps per square meters. And it should be the switching times below 10 nanoseconds. For the STT element, here the smallest one, one of the smallest one, you see here switching times of 3 nanoseconds with a moderate current density and therefore a relatively good duty cycle. For an SOT element with a little bit larger size, you can achieve switchings also below a nanosecond, but you see the current density are relatively high, especially for fast switching, which results in a very low and bad duty cycle. Very recently, a combined SOT-STT element was presented here with a relatively complex structure, and here the switching of 200 picoseconds is achieved with a very low, astonishingly low current, but this you have to compare with the complex elliptic size, and this ellipse is very, very large. So this is correlated to these low current densities, obviously. Let's come to the next famous solution. This is the well-known magnetic domain wall racetrack memory proposed about 13 years ago. What happened with this in the meanwhile? The citations are extremely high. So the last article or recent article is here, are the results shown. And here the authors want to increase the speed of the domain wall. You see it here, how they move, via a dusting of the interfaces of palladium, platinum, and so on. What you see here is that the current densities to move this domain wall with a relatively low speed of maybe 100, in the best case some 100 of nanometer per nanoseconds, with extremely high current densities. And these are still planar. There is, to my opinion, no way to grow this via magnetosputtering in 3 dimensions, and the current densities are so high that this system will, I think, it will not work from the point of view today. But you can change the system to have much higher domain wall velocity. This is here a modified gadolinium gallium garnet GGG, on which with well crystallinity you can grow here a modified YIG sample, and the current densities are also in the order of 10 to the 12 amps per square meter, a little bit lower, but the speed is extremely high. The drawback, or you see here the values, this performs, to my opinion, much better, but the garnets are at the moment the only well-working magnetic insulators. They require perfect crystallinity, only possible on GGG. They are extremely hard to nanostructure, and to my opinion, there is no chance, at least at the moment, for a large scale production. So this is a model system only. So let's go to the next solution, the Skermian Racetracks. Every one of you knows these features. They are induced by a new interaction, the DMI, and you can make some plans to conduct these Skermions on a wire and to read out the 1 or 0 electrically. They are often multi-layers. You see here how they look like. I don't know exactly what here should topology mean. And the currents are a little bit lower than 10 to the 11 amps per square meter, which will destroy the device. They are very slow. The threshold current is strongly temperature dependent, because these high currents will heat up your system immediately. You see here moderate current densities, extremely low speed. The pulse times have to be very long. That's why the duty cycle is 5%. And these are our measurements via X-ray transmission. You see here they move as they want. They are trapped by defects and so on. And this shows you that with such a device as shown here, a Skermian racetrack, it makes no sense to try to realize it. We had to finalize a PhD in 2018 where one chapter was Skermion imaging, and it was hard to extract some values of DMI with contradicting results depending on the model. And in this frame we looked at the Skermian systems published up to now, and we saw that any of these 37 publications have their own recipes for Skermian systems, and this shows us that every lab has different recipes to create these Skermions, which in our view made the Skermian physics behind a little suspicious and critical. To interpret the Skermions or any magnetic structure on the nanoscale, we looked at the basic equations. Everyone knows the LLG equation. Here is the main value, the effective field, and the effective field depends on energy terms, normally 4, exchange, dipole, anisotropy, and DMI. And in these energy terms go in magnetic parameters as the saturation magnetization, the exchange constant, the DMI, and the anisotropy constant. The critical thing behind this is that the exchange energy is extremely short range and the largest one. Then the anisotropy and the DMI are also short, but they are normally governed via the dipolar energy, which is small but is very long range and adds up to normally a high value and depends on the real structure and geometry and morphology of the system. But we were in a lucky situation that we have one system, a tantalum, coffee B, MgO multi-layer systems, where we have a wedge of identically prepared samples which have been very large. The variation of the coffee B thickness was from 0.8 nanometer to 0.4 nanometer, and here are a typical picture with our transmission X-ray tachography. Here we found only for the thickest system at a relatively high field Skermions, and it was really hard to interpret this. And then I lose my nerves, and then I said, we have really to look what are these parameters in these reduced dimension for these systems I showed you before. So the task was to determine as function of thickness the saturation magnetization, the anisotropy energy, and the exchange energy. What you need for this, you need an excellent SQUID VSM device. Then you need very large samples, otherwise you cannot measure the magnetization and so on. Then you need excellent experimentalists who can deal with SQUID measurements with low material amounts. Therefore, you need also much time and diligence to measure the saturation magnetization, the anisotropy energy, and all as function of temperature. After about 3 months, we have gained the following results. So you see here, the Curie temperature as function of thickness is reduced by a factor 3. The saturation magnetization, which is itself temperature dependent, reduces from 14 angstrom to 8 angstrom by a factor 5. The exchange constant, also temperature dependent, reduces by a factor 10, and the K effective peaks at 12 angstroms. The K effective itself is in the energy range around room temperature, also strongly temperature dependent. So you have to take care what value you take, and you have also to know the temperature of your system during the measurements. So based on these measurements, we looked at, is there possibly a dead layer, which is often taken to explain the reduced saturation magnetization from extrapolation of the magnetization as function of thickness and temperature. We saw here this behavior. An extrapolation, a linear extrapolation, shows that we have a linear fit. This means at zero temperature we have no dead layer, and these dead layer are strongly, so-called dead layer, are strongly temperature dependent. This shows you that the magnons excited at the interface will reduce this, so that layer may be interpreted in that way, but it depends on temperature. And the magnetic layer, or the non-magnetic contribution, or the reduced magnetization, would result in such an estimation of the layer, of the dead layer. And now you have to look where is it in these strong disturbed interfaces. And by the way, we have a total thickness of 87 nanometer and 86 nanometer, and this brings me to an old story. We have done a lot of vortex studies, and you see here permalloy is also a fruit fly for magnetism. You see here the phase diagram for a permalloy vortex formation as function of radius and thickness, and in a wide range you have here the appearance of a vortex. But what is the truth? So if we increase the thickness and the radius, we have at that value shown here also a vortex. But if you increase the thickness even more to 180 nanometers, then you see no vortex anymore. Permalloy is oriented perpendicular to the plane. Where does this come from? You have to do careful TEM measurements. You see here a 7 nanometer permalloy. It is very granular, so you have here a lot of defects and interfaces, grain boundaries and so on, which results, if you increase the thickness, in a columnar structure. And this means that the internal structure of a simple permalloy will increase at a certain thickness, or with increasing thickness the anisotropy is so high that you have found no vortex up, I would say, up for more than a thickness of, let's say, 150 nanometer. This is well known. This is an old story. This shows you that not only the interfaces, but only the grain boundaries, the inside grain boundaries, will influence your magnetic parameters very strongly. Very famous at the moment are van der Waals flakes. Is this the solution? Therefore, we have looked at the fruit fly for ferromagnetic van der Waals systems, FGT, which is grown in these layered structures. And you see here for the basic crystal, the Curie temperature is about 220 Kelvin. You can increase the Curie temperature close to room temperature if you increase the ion contact, but then you lose also the van der Waals properties. Here are our X-ray transmission measurements. The advantage what we have with X-ray transmission, we can do also spectroscopy, which shows you the following. For this system, we have at the moment already better systems, but for this system with a thickness of less than 25 nanometers, it is completely oxidized, and for about 60 nanometer we have a very good flake with the expected high magnetic ion moment here determined by XMCD. So we get here with our method directly the information on the ion valency, the oxidation state, the magnetization and the sample thickness. Here are more systems, more studies. You see that you found here in between 150 and close to the Curie temperature the formation of the Skermions. And what is astonishing is that the magnetic structure depends not so much on the total thickness. We are just preparing a paper for this, where we compare this also with micromagnetic simulations. What is the advantage also of our method? We can do local hysteresis loops, because these flakes you cannot measure by squid. They are too small, too low masses. And here a funny experiment in the field-cooled case. You have here at 125 Kelvin, you have here you can start with Skermions, which become more and more dense, and then they have here these soap-like structures. If you watch the preparation of these van der Waals systems, then you know that these are individual flakes. They are nearly perfect concerning the interface, because they have really a van der Waals surface, but it is a long way to integrate them into a device, because they are prepared at the moment highly individual with unforeseen thickness and dimensions. But you see here they are very nice Skermion systems. The Skermion phase diagram is very tiny. These are not Skermions, we identify them as Skermion bubbles. They are really nice objects to do basic science for magnetism, but as I said already, the way to have them a solution for the problems, the present problems in spintronics, is also a large road, a long road. Now I'm at the end. I give you some comments for the spintronics for future. So are they ultra small? They are not ultra small. The device bit density is limited due to the dense current lines, and 3D architecture is very difficult. Ultra fast, they are not so fast. This is known already from the MRAMs, because high switching speed requires very high current. The ultra low energies, this is also not true unless we can reduce the write and read current very significantly. Maybe they are non-volatile. The high endurance is, to my opinion, also questionable, because you have strong danger of electromigration due to the relatively high current. And don't forget, the silicon competition or CMOS competition is very strong and fast, because this gives you the periodic table. Silicon is an excellent material available at single crystal. It's a natural semiconductor. It has sharp interfaces. It is very cheap and handsome in preparation. And the oxide could be also piezoelectric, and there are much more properties which make silicon an outstanding candidate for nanoelectronics. Spintronics for future. What are the challenges and the personal comments? Maybe you know it already. The reduction of the current density is extremely important in nearly all spintronic elements and devices. And how we can do this? We have to improve and to control the layer quality. In any case, we have to reduce the facts, and we have to control the stack design, and this is difficult with magneton sputtering. This is also correlated because we don't know the real structure. We don't have a fundamental understanding of the underlying very beautiful physics and these fascinating phenomena. Maybe there are new classes coming up as oxide, chalcogenides, also magnetic semiconductors, perovskites, and so on, but they are normally difficult to and nearly impossible to integrate into devices based on CMOS and so on. This will take a long time and is possibly impossible. So we need, in any case, more serious studies with consequent structure control and wide-spanning structural and magnetic characterization on the nanoscale. It is urgently necessary to make TEM images, to make very reliable magnetization measurements, to have reproducible systems. And I can combine it. We need more serious scientific investigations and less unserious problems. In nearly any paper concerning spintronics, it is written that this is a promising route to beyond CMOS. At the moment, this cannot be seen. So let's, at the very last end, show you some history of spintronics. We started with the GMR Nobel Prize. The first experiments were in 1984. Then, just at the end of the last millennium, the spin transfer torque arrived. The MRAMs have been proposed since more than 20 years. The racetrack memory was proposed, but I think it will never work. SOT is maybe in some cases a solution. Skermions, I think there is at the moment no way seen how to implement or use this for any device. And the van der Waals systems are very, very new, and they have, in terms of preparation, their own challenges. So we don't know at the moment, to my opinion, where to go. And with this, I thank you for your attention.